Math 422 Final Project Heart Disease Prediction. According to the Centers for Disease Control and Prevention, the leading cause of death in the US in 2021 was heart disease, killing approximately 695,000 people. In fact, 1 in every 5 US deaths is attributed to heart disease, which averages to approximately 1 death every 33 seconds. This wasn't always the case. At the beginning of the 20th century, heart disease was decidedly less prevalent, though lack of accurate medical diagnosis may be a factor in vital statistics. Heart disease seemed to increase as lifestyles became more sedentary, tobacco use increased, and dietary changes resulted in elevated cholesterol levels. By the 1950s, heart disease was the leading cause of death in the US. Mortality rates from heart disease peaked in the 1960s before plateauing. Despite recent healthcare innovations and improvements, as well as healthy lifestyle initiatives, the percentage of deaths from heart disease has been steadily rising again over the last 30 years, and the number of people under 50 with heart disease is also increasing. The term heart disease refers to any condition which affects the structure or function of the heart. There are more than 30 different types of heart disease, including but not limited to coronary artery disease, heart arrhythmias, heart failure, and pericardial disease. Some types of heart disease are congenital, meaning occurring from birth. However, most heart disease is developed over time and is preventable through healthy diet, regular exercise, and the abstinence from harmful chemicals such as tobacco products. While heart disease is incurable, it is treatable through modern medical interventions such as surgery and through lifestyle changes such as diet and exercise. Early detection is a key factor in the successful treatment of heart disease. The earlier heart disease is detected and treated, the less damage is done to the organ and the greater the life expectancy of the patient. Traditionally, heart disease detection techniques have been costly and only available in areas of the world where there is ample healthcare availability. X-rays, electrocardiograms, and angiograms are examples of some of the tests doctors regularly use to detect heart disease. Despite their accuracy, it is not economically or physically feasible to perform regular tests using such methods on every patient that could potentially have heart disease. Thus, a screening method is needed to predict whether a patient has heart disease or not, filtering the pool of patients for further testing. There are various screening methods that have been developed. One of those methods is using a logistic regression model to predict whether a patient has heart disease or not, based on a selection of the patient's attributes. As with all predictive models, there is always a margin of error, so the developers of the model must determine how to reduce that margin as much as possible through appropriate attribute selection and by adjusting the parameters of the model to increase accuracy. As there are already complex models being used in the screening of patients for heart disease, our project aims to replicate one of the basic predictive methods that others have previously used. Our goal is to create a logistic regression model to predict whether a patient has heart disease or not. By doing this, we aim to show that even a basic screening model can be beneficial in predicting heart disease, thus helping healthcare professionals to identify and treat patients who are at risk from this life-threatening condition. There have been many studies focusing on building models with the intent of improving screening for heart disease. Logistic regression is an example of a prediction model that has been used often to predict heart disease. In a study conducted by the East-West Institute of Technology in India, a logistic regression model was used to predict cardiovascular disease with an 87% accuracy rate. We have based our own project on this model as it is one of the simplest models to create. Other researchers have used more complex methods such as decision trees and neural networks. A study conducted in Poland focused on comparing the performances between these three models, logistic regression, decision trees, and neural networks. They compared the model's sensitivity, the ability to identify a patient with heart disease given the individual truly does have the condition, specificity, the ability to identify a patient without heart disease, given the individual truly does not have the condition, and accuracy, the ability to differentiate the positive and negative cases correctly. The study found that while the three models were similar, artificial neural networks had the lowest error rate and the highest accuracy. Thus, the authors concluded that artificial neural networks was the best technique to use for that particular dataset. Some studies aim to predict the presence of multiple heart diseases, such as a study presented at the 2020 Fourth World Conference in London, which used multiple complex, smaller models in conjunction with each other, while other studies focus their models on individual heart diseases, such as the study of macrovascular disease in Caucasoid diabetic subjects, which aim to identify and analyze common risk variables. Having a broad model encompassing multiple heart diseases may be beneficial as an initial screening for large groups of individuals, while singular models may be helpful on a smaller scale to screen focused groups that may experience additional health issues. Other studies focus on analyzing and improving attribute selection methods, as most models include no more than 14 attributes. A study performed in Pakistan used feature selection techniques and algorithms to improve a heart disease prediction model's attribute selection process, resulting in improved model accuracy. The authors did acknowledge, however, that model developers would need to account for the ease of obtaining various attributes to decide whether the increase in accuracy is worth the cost or difficulty incurred by obtaining the attribute information, especially in less affluent geographical locations.
We sourced our data from the UCI Heart Disease Database. This data was originally collected for a 1989 study by DeTrano et al. In the American Journal for Cardiology. The data we use in our study was slightly modified from this original dataset and obtained through Kaggle. In this modified dataset, we obtained data that had only 16 of the attributes out of the 76, as we'll discuss shortly, in the original paper. Kaggle has an additional 2 data points, including a unique ID number and the geographic location of the data. Speaking of geographic location, the data we used was sourced from multiple physiogeographically disparate regions. Preliminary data in DeTrano et al. Was collected from the Cleveland Clinic in Ohio. Data used to verify their studies was also sourced from Long Beach Veterans Affairs Office in California, the Hungarian Institute of Cardiology in Hungary, and the Basel and Zurich University Hospitals in Switzerland. We do not use this data because it hampers the generality of our model and thus reduces our ability to predict future instances of heart disease in populations outside of these locations. To the right, you can see the metadata regarding the locations as well as the sample counts from these locations. Given that the original dataset has 76 attributes and that we do not have a deep understanding of all of these attributes, we chose to use the 16 present in the Kaggle dataset. After stripping away the ID number and the geographic region from the data, we are left with the 14 most studied attributes in this dataset. Given that we wish to make a universal model, we did not use any of the sparse geographic data and figured it may be harmful to our predictiveness in other circumstances. We also later removed attributes displaying multicollinearity in future tests of our model. To be precise, we used the sklearn logistic model as outlined in the 1.3.2 version of their API. We used their liblinear solver, which is adequately adjusted to small data sets, and we chose a 1 versus rest classification objective. Additionally, we chose to use balanced class weights, and all other parameters were left at their defaults as of this version of sklearn. When it comes to judging our model, we chose accuracy for the main performance metric. Additionally, we chose to compare the weights assigned to each attribute against existing medical literature. This verifies that the model correctly correlates certain characteristics with heart disease over others.
We carried out our experiment using Google Colab running Python 3.10.12. The UCI heart disease dataset available on Kaggle was what we used to test and create the models. To prepare the data, we removed all null values. Null values are missing attributes within a tuple, which can be detrimental for regression, as you can be attempting to gain insight from unknown values. From the red figure on the right, it can be seen that all null values in the dataset have been removed. As the variables that we are using, many of them are categorical instead of numeric, so we use dummy variables to allow for the creation of a logistic regression model. There are also 4 types of heart disease present in this dataset, and this model only tries to determine if they have one of those 4 types or no heart disease, so we combined all types of heart disease together. Our first model was created using sklearn to create a logistic regression model to predict the chance of having heart disease. This model showed that the most impactful positive variables on predicting heart disease were reversible defective maximum heart rate, having exercise-induced angina, being male, and every unit increase in the number of major vessels colored by fluoroscopy. Having these variables present increased the chance of a person having heart disease. Having chest pain type non-angina and having a fasting blood pressure greater than 120 reduced the chance of having heart disease. Overall, the model had an accuracy of 87% when predicting heart disease on our test data, which is quite high. We wanted to check that our assumptions were met for logistic regression. However, we discovered an issue with multicollinearity. We found that there was multicollinearity occurring among age, resting blood pressure, cholesterol, and maximum heart rate achieved. This can be seen as the VIF factor for these variables is above 10, showing extreme multicollinearity. For our second model, we removed all the multicollinear variables except for age. There are not many major differences in what was the most significant variable predicting heart disease. However, the coefficients did change slightly. This new model had an accuracy of 86.7%, which is again quite high for predicting heart disease with these given variables. Checking the assumptions for our second model, we found that there were no major issues with multicollinearity. This was an expected result, as the new model had the multicollinear variables removed aside from age. This means that the assumptions for logistic regression were met. These assumptions include independent observations, a binary response variable, no extreme outliers, and a sufficiently large dataset.
The above table shows the comparison in accuracy between all the studies. In some studies, logistic regression was the only technique used. Accuracy can vary for multiple reasons, including things like the ratio of the train test split, weight assignment, and other configurations or specifications. Our logistic regression model, when compared to the 4 other methods, falls above the average in terms of accuracy, at around 86.7%. In this study, we created a logistic regression model based on the UCI heart disease dataset to predict heart disease in patients, using accuracy as the primary indicator of performance. After creating our model, we noticed there was multicollinearity between age, cholesterol levels, resting blood pressure, and the presence of thalassemia. As these were not able to be combined, we removed these from our model, leaving us with only 10 attributes. But even with only 10 attributes, and only using basic logistic regression, we were able to achieve an accuracy of 86.7%. With this being the only measure of performance, when compared to other models which use this dataset, our model was of comparable performance. This is significant, as our findings show that machine learning models, even when not overly complex, can be used to help screen patients for heart disease, which is important as early detection aids health professionals in treating patients successfully through life-saving interventions and treatments.